Hello everyone, my name is Richard and today we're covering proof in A-Level Maths and we'll go through absolutely everything that you need to know. There are 4 key elements of proof that you need to be aware of. Those are proof by deduction, proof by exhaustion, disproof by counterexample, and proof by contradiction. And we'll kick off with proof by deduction. So proof by deduction is essentially proof by a series of logical mathematical steps or arguments. This is the most common type of proof that you're going to come across, and it's relatively straightforward. There's not sort of huge amounts of theory that you need to know. It's just about thinking things through carefully and making sure you get lots of practice. So if we kick off with an example, so in this case we've got prove that n cubed minus n is a multiple of 6 for all integer values of n. So how are we going to tackle this? Now, well, first of all, we can see that in the question we've got the word multiple. So instantly when I've got an expression in n, I'm thinking, okay, can I factorize this? And yes, I spot straight away n is a common factor. We can take out n. And then we can use a further trick that n squared minus 1 is equal to n minus 1 times by n plus 1. So this is using the difference of 2 squares. Put the formula up on screen. So that's knowing that a squared minus b squared is equal to a minus b, a plus b. Don't forget that trick because that comes up all the time. It's super useful to know. So now if we take a look at what we've got n times by n minus 1 times by n plus 1. That is actually, we can spot that's the product of 3 consecutive integers. So if it's the product of 3 consecutive integers, it must contain one multiple of 3, and it must also contain at least one even number. So that we know straight away that we've got factors of both 2 and 3 within this expression. And that therefore means that we've got our multiple of 6. And as long as we sort of write that down, our argument down nice and clearly, that's job done. Another classic example would be proof that n squared plus n is even. We can factorize that to be equal to n times by n plus 1, i.e. the product of 2 consecutive integers. So one of them must be even, and therefore the product must be even. Moving on to our next topic, so that's proof by exhaustion. Now, in a lot of cases, proof by exhaustion would not be practical. So considering the previous cases we looked at, where we had to prove something for all integer values of n, it wouldn't be practical to go through every single case. In fact, it would be impossible. So proof by exhaustion only works in certain cases where there are a small number of cases that you need to prove a statement is true for. Essentially, what we're looking to do with proof by exhaustion is prove that the statement is true for every single individual case. This is best demonstrated by working through an example. So if we consider the problem, given that p is a prime number, such that 3 is less than p, which is less than 15, prove that p minus 1 times by p plus 1 is a multiple of 12 for all integer values of p. So there's a big clue in the question here that because p is restricted to a small number of values, that proof by exhaustion is the way to go. So if we start by listing the primes, so we've got 5, 7, 11, and 13 as the primes between 3 and 15, and we can work through each of these cases taking the product p minus 1 times by p plus 1, and in each case demonstrating that the product is indeed a multiple of 12. Note that in the question that p is strictly greater than 3, and therefore we don't need to consider 3 within our list of primes. And that's the complete solution to this question. We don't need to do any algebra in this case because it's proof by exhaustion. We just need to work through each individual case carefully, making sure that you don't make any silly arithmetic errors. So that brings us on to topic 3, and this is actually the opposite of what we've been doing so far. In this case, we're looking to disprove a statement. That's disproof by counterexample. And the trick for disproof by counterexample is that we only need to find one counterexample for the statement need to be false. So we need to try and be as quick as we can to identify a counterexample that disproves the statement. Again, this is best illustrated through an example. So if we consider the case where we've got n cubed minus n plus 7 is prime, and we're looking to disprove this statement. And the quickest way to get to a solution here is actually just to spot that if we plug in n equals 7, then all of the components of this expression are going to be a multiple of 7, and therefore the expression as a whole will also be a multiple of 7, i.e. it cannot be prime. And therefore we found our example, and that is sufficient to disprove the original statement, and we can move on to the next question. Interestingly, if you hadn't spotted n equals 7 and just started working through different cases such as n equals 2, 3, 4, etc., it wouldn't be until you got to n equals 6 that you'd found a case that wasn't prime, and you'd potentially spend quite a bit of time on the intermediate calculations along the way. So that brings us on to the fourth and final proof topic that you need to know, and that's proof by contradiction. And this is probably the key one where actually there is some bookwork to know. There's a couple of examples that you just need to commit to memory. The first step is to assume that the original statement is false, and then in step 2 we're going to work through the implications of that, assuming the statement is false, and show that that actually would result in a contradiction. And if we can find that contradiction, then we can therefore finally deduce that the original statement must in fact be true, and then that's the proof complete. So those are the 3 key steps that you need to know in general to prove something by contradiction. But there are 2 examples in particular that are in the specification that you just need to learn and commit to memory. The first of those is prove that there are infinite prime numbers. So to do that by contradiction, we first of all assume that the statement is false, i.e. that there are actually a finite number of primes. And if that is the case, then we could list those primes as P1, P2, P3, etc., all the way up to Pn for some finite number n. The next step is the key step to remember. So if we consider the product of all of these primes put together, so P1 times P2 all the way up to Pn, and then we add 1. And if we consider that number, then that number can't be prime because it's much larger than any of the individual primes on our list, and therefore, if it's not prime, it must be divisible by one of the primes. However, we can see that because we've added 1, it can't possibly be divisible by any of the individual primes, because each of them would have remainder 1. So that therefore gives us our contradiction in this case, and we can therefore go back to the original statement, and we've shown that actually that must in fact be true, since if it were false, we would reach a contradiction. That's the first example to know. The second one is prove that the square root of 2 is irrational. So again, it's just a case of following our process. So first of all, we assume that the statement is false, i.e. that the square root of 2 is in fact rational, and if it's rational, then we can express it as equal to a over b for some integer values a and b, where a and b are co-prime. What that means is that they have no common factors. So if we write this expression down, squaring both sides, we get that 2 is equal to a squared over b squared, so 2b squared equals a squared. And that means that a squared must be even, since it has a multiple of 2. And if a squared is even, then a must be even. And that's using that an even number times an even number is even, and an odd number times an odd number is odd. So if a is even, then we can write a equals 2k for some integer k, and plugging that back into our expression above, we get that 2b squared equals 2k all squared, i.e. 2b squared equals 4k squared, and dividing both sides by 2 gives b squared equals 2k squared, which is exactly what we had above, but for a. So we can conclude that b squared is even, and therefore b is even. But if b is also even, then that means that both a and b have a common factor of 2, and that actually is a contradiction to our original assumption above, where we assumed that a and b were co-prime. So that gives us the contradiction we were looking for, and therefore the original statement must in fact be true. There are similar examples that may come up in the exam. So for example, prove that root 3 is irrational would be a very similar case, but using 3 instead of 2, and demonstrating that if a squared is a multiple of 3, then a itself is also a multiple of 3. So that covers everything that you need to know to ace the proof topic in your exam. If you have any questions on proof, or if there are any topics that you'd like me to cover next, please let me know in the comments below. Make sure to like and subscribe to the channel. See you in the next video. Goodbye.